Hello everybody and welcome to our webinar. My name is Vladimir Podnos. I am Director of Marketing and Support here in Terra Analysis, and after my short review of QuickField core functionality and simple ways to expand it, our support engineer Alex will show you free QuickField tools, which were originally developed as small custom programming projects on our customers' requests, and then we found them useful enough to be offered to everybody for free. So, for those who never seen QuickField before, I am displaying this slide with list of QuickField analysis capabilities. As you see, our range is very wide. It includes electrostatics, DC, IC, and transient conduction, several types of magnetics analysis, heat transfer, and stress. These formulations may be used separately or in combination, where results of one analysis are used as initial settings for other analysis. And what is most important, all these types of analysis are performed with very high speed. And regardless of how complicated this is geometry and how large the finite element mesh, you may get results extremely fast. On this slide, you see the plots of solution time versus the number of mesh nodes. As you see, it is quasi-linear and requires minutes on our largest meshes. This proves that QuickField is extremely powerful and rich of features. But what if you need a feature which is not available? For example, you need to prepare a PowerPoint presentation with field results calculated in QuickField. Starting QuickField, adjusting display settings, copy picture, switch to PowerPoint, and paste it here. Done. For one-time task, it's okay. It is simple, straightforward, but situation changes if you need to repeat it hundreds of times. Then some special tool for automation will save you hours. With QuickField, it is also possible. Feature missed in our core user interface may be implemented as a separate utility which interacts with QuickField core via application programming interface. PowerPoint picture import automation is the job for one of three utilities which we will show later today. External procedures may be written in Visual Basic for applications, which is part of Microsoft Office. You may use MATLAB, you may use Visual Studio, you may use plenty of different programming systems. Some of QuickField components are also based on this technology. For example, parametric analysis tool label mover is external application. It's not a QuickField core. Add-ins in QuickField tool menu are also external applications. We provide access to our internal data structures and functions via object-oriented interface, which is called ActiveField. It is fully documented, and in the programming section of QuickField website, you will find plenty of examples and templates. Today we will show you some free tools which are based on ActiveField. A full list of free tools available today is listed on our website. But we don't have time to discuss and show all of them, and today we will show you just few. These tools may be considered as templates as examples of using our application programming interface, but in the same time they are ready to use tools, and they quite straightforward. My colleague Alex will show you today how to bring pictures from QuickField to make animation in PowerPoint, how to use the results of the stress calculation and bring back the deformed shape of the model to repeat analysis with changing geometry, how to use how to calculate a linear contour in cylindrical problem, and how to find the interaction between cylindrical permanent magnets in 3D formulation. So, Alex, please continue.
The first tool we will review today is the animation to PowerPoint. Animation to PowerPoint simplifies the picture export from QuickField results to PowerPoint presentation. It supports time harmonic problems, AC magnetics, AC conduction, and transient problems, transient magnetics, transient electric, and transient heat transfer. For transient problems, the field picture is copied from each time step, and for time harmonic problems, the field picture is copied every 10 phase degrees in the range from 0 to 360 degrees. And each picture is inserted to separate slide of the presentation. This tool is very easy to use. So here is the simple case. This is the pulse transformer. The transformer consists of the steel core and the windings, the primary winding, the secondary winding, and the tertiary winding. The voltage pulse is applied to the primary winding, and the current begins to flow in the windings. Let's start QuickField and open this case. Here is the QuickField and the simulation problem. The problem type is transient magnetics. This is the geometry model, primary winding, secondary winding, tertiary winding, the steel core, and the air. There is the air gaps here to increase to reduce the inductance. And there is the electric circuit. This is our transformer, and our transformer is connected to the electric circuit. The voltage pulse is applied to the primary winding. Now let's take a look at the simulation result. I will adjust the field picture. I will switch on the flux density and the vectors of the magnetic flux. Now here is the magnetic flux distribution at some moment of time. We can watch how we started with the zero magnetic field distribution, and we can watch how the process develops on the field picture. I applied the pulse, the voltage pulse, and the current begins to flow. And we can see how the process develops in the electric circuit. So this is the electric circuit, the primary winding. The voltage pulse is applied to the primary winding, and the current begins to flow. So when the pulse is finished, the current fades to zero. So my task is to copy every picture that represents the field distribution at each moment of time, from QuickField to the PowerPoint. To perform this task, I will use our free tool the free tool Animation to PowerPoint. To use this tool, you should run QuickField and run PowerPoint. So this is our tool. And to import pictures, I should open QuickField problem. It is already done. Adjust the field picture. I switched on vectors and the flux distribution. Then you should run the presentation and then press the Import Pictures button. And the import begins. Let's take a look at QuickField. You can see that in QuickField the results are iterated from in every moment of time, and the picture copied from QuickField to PowerPoint. So here are the pictures copied from QuickField to PowerPoint. Now in PowerPoint you can see how the process develops. Next tool I would like to show you is the StressDeform shape. Again, the same pulse transformer. And now the mechanical force is applied just above one of the legs of the transformer. Naturally, the transformer core deforms. And our task is to find out how this deformation affects the magnetic field distribution. So first we should simulate the stress analysis problem. I will start QuickField and open the stress analysis problem. Here it is. You can see the geometry model. In the stress analysis problem, I will simulate only the steel core and calculate the deformation in the core. So there is only one object, the steel core. Other blocks are excluded from the calculations. I specified the mechanical properties for the steel core. The bottom of the core is fixed, and the force, the mechanical force, is applied here. This is the mechanical force. Now let's simulate this case and take a look at the result. This is the deformed shape and von Mises stress distribution. If we open the field picture properties dialog, you can see that the deformed shape, the deformation is magnified. Actually, it is not this great. Let's take a look at the 10 times scale deformation. Again, 10 times scaled. You can see that under the applied mechanical force the core is deformated. Now I will use our free tool, the StressDeform. And with this tool I will modify the geometry model file using the stress analysis simulation results. So I start this tool. The tool asks me to close all problem windows and open and solve the transient analysis problem. It is done. Then I should press OK to transfer deformations from the results to the model. I press OK. Now the transformations are transferred in the geometry model. When the transformation is done, we can see the dialog offering us to save the transformed model. Now here is the transformed geometry model. Let's simulate again the magnetic problem and find out how this transformation affects the magnetic field distribution. Again, I start QuickField and choose the deformed geometry model. Here is the deformed geometry model. It looks pretty the same as the unloaded model, because the deformations are really very small. But let's take a look at the simulation result. Here I'm solving the transient magnetic problem, and you can see the field distribution. I will open the previously calculated original problem. Now the left is undeformed shape of the core, and the right is deformed shape. The deformation was very small, but nevertheless there is the change in the magnetic field distribution. The air gap here is a bit smaller than the air gap here, so the field distribution is not symmetrical anymore. The model, as you see it on the screen, is always plane, and this plane model represents three-dimensional object. The object shape depends on the model class. For plane parallel model class, the three-dimensional object is the infinitely long in z direction, behind the screen plane. For axisymmetric problem, the three-dimensional object represents some kind of cylinder. Axisymmetric formulation is useful when you simulate cylindrical objects like tubes or coils, and here is the simple coil with the core simulation example. In the geometry model in QuickField, you should draw only the upper half of the cross section. I will start QuickField and show you how to simulate this case and how to change the model class. Now this is the QuickField. I open the problem properties dialog and you can see that the model class is axisymmetric. Now let's open the geometry model. Here I have the core and the winding. And outside the coil there is the air. Now let's take a look at the simulation results. Here you can see the field distribution in the coil. In QuickField, when you're analyzing the results, you can build contours and get the field distribution along the contour. Here I build the state contour, and this is the flux density distribution. And the same values I can see in the table. Here is the table of the field values distribution along the contour. This is the contour coordinates, and these are the field values: flux density, current, electric potential. Again, we see the plane picture, and in cylindrical simulation, in cylindrical model class, every edge represents cylindrical surface or disk surface. And every point represents the circle in the three-dimensional world. But what should I do if I need to get the field distribution along the straight contour that is not aligned with the axis of the rotation? I got the coil simulated with the axisymmetric formulation, but the straight contour does not conform the axisymmetric formulation. We offer the simple tool that can convert coordinates from the Cartesian to cylindrical and list the field parameters along the contour. So in this simple case I need to get the field distribution along this contour. Here are the contour coordinates and Cartesian coordinates. I will start our free tool. In our free tool you should specify the Cartesian coordinates of the contour beginning and the end point. And specify number of divisions. And these are the results. On the left you can see the Cartesian coordinates of the points distributed along the contours. There are 20 points, and these are their Cartesian coordinates. These are the coordinates of the same points converted to cylindrical system, and these are the field parameters distributed calculated in these points. For magnetic problem, these are the magnetic flux density components. So it works pretty the same way as you get the field distribution in QuickField. The only difference is that in QuickField you can draw the contour using graphic user interface, and this will be only the cylindrical contour. And with our tool you can specify the contour coordinates in Cartesian system. Next case is the force calculation between arbitrary posed cylindrical permanent magnets. Generally, to solve this problem you should run three-dimensional magnetic simulation. But in some cases this test could be simplified. Some kind of magnets, practically neodymium thermal magnets, features magnetic permeability very close to the permeability of the air. And this allows to use superposition principle. First we calculate the magnetic field produced by the first magnet. Then we calculate the magnetic field produced by the second magnet. And then we can find the vector sum of both fields. And this approach is implemented in our free tool. Let's take a look at the practical example. There are two coaxial permanent magnet cylinders. The cylinders are magnetized along the axis of rotation. In this case we can simulate in QuickField using axisymmetric formulation. So I will start QuickField. Here's the magnetostatics problem, and the model class is axisymmetric. In axisymmetric model you should draw only the upper half of the cross section. So I have two magnets here, magnet 1 and magnet 2. And for each magnet I specify the permeability and the coercive force. Now let's take a look at the simulation result. This is the magnetic field produced by two cylinders. And our task is to calculate the magnetic force acting on each cylinder. To calculate the force, I build the contour around the cylinder. And follow to the integral list. This is the mechanical force acting on the left cylinder. fact, to calculate the force, QuickField integrates the values along the contour, not across, but along the contour. Here is the equation that is used to calculate the magnetic force in QuickField. Now let's use our free tool on this simple case. What should we do here? We should specify the permanent magnet cylinder's dimensions and position in space. So we specify the coordinates of the points at the bottom and the point at the top of the cylinder. Also we specify the coercive force and the magnetic permeability of the material. And we should specify the coordinates of the integration contour. The integration contour here is depicted with the orange lines. Here the coordinates of this integration contour are specified. Now I press the calculate button. At first, QuickField is invoked to build the geometry model of the first cylinder and calculate the magnetic field distribution produced by the cylinder along this contour. Then our tool invokes QuickField to build the second cylinder and calculate the field distribution produced by the second cylinder along this integration contour. So each cylinder is simulated and its magnetic field is calculated. The total magnetic field is calculated as a vector sum of the magnetic fields produced by each cylinder. Then the Maxwell tensor integral is calculated along the integration surface. That gives us the magnetic force acting on the volume surrounded by the integration contour. So here is the result. Force acting between two collinear permanent magnet cylinders. Let's compare this value with the value calculated by QuickField. Here I have two cylinders simulated together and can calculate the force. I build the integration contour and QuickField then integrates the field values distribution along the contour. So we have verified the results calculated by our free tool, and you can use it to calculate the force acting between a number of arbitrarily placed permanent magnet cylinders. On our website you can find several examples of calculating force between permanent magnet cylinders.